Hello and welcome to today's video where we're looking at gravitational fields. So before we talk about gravity specifically, we need to define what a field is, because we'll be looking at gravitational fields in this video and the next couple, and then after that we'll be starting to look at electric and magnetic fields. So it's helpful to come up with a definition of what a field is. So a field, or sometimes called a force field, is just an area of space, so it's just a region where an object experiences a force. And the most common of these that we know about from everyday experience is gravity. So for example, if we took a mass and we put it up here, it would experience a force because it would fall down. Now, we can represent gravity pictorially. So we've got two different types of fields here. So here we've got a planet, and we're able to draw on these field lines. Now the field lines show what would happen to an object if it was placed at that particular position. Now, so for example, if we placed a mass here, it would move in this direction towards the center of the Earth. So it moves in this direction, which is why the arrow is pointing in there. If it's over here, then it would point this way. So they all point towards the center of this planet. Now this particular type of field, where all of the lines seem to radiate from the middle of a particular object, is called a radial field. So that's a radial field, where all the lines seem to, they're a little bit like spokes on a bicycle wheel. So that's called a radial field. If we look at a really, really small portion of this planet's surface, and we zoomed right in, then we'd basically see the surface as being flat, just like we do on the Earth. And in that case, all of the field lines would look as if they were pointing in the same direction. They're actually not. It's just that the planet is so big that we can't tell the curvature of this, and so therefore we can't tell that they're going in different lines. So when we're actually very close to the surface, then we can consider the field not to be radial anymore like this. We can consider this to be what's called a uniform field. So this is a uniform field because all of the lines are equally spaced. They're all pointing in exactly the same direction. Now, one really, really important thing about the pictures of these is that the closer the field lines are, the stronger the force that an object feels. So you can see here that the field lines are closer here than they are out here. So the gravitational force here is stronger than it is out here. And we can tell that simply by looking, because these field lines are closer together. For a uniform field, that's not true, because all of the spacings are all the same, and so therefore it doesn't matter where you put a mass, whether you put it here, 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 up here, down here, it'll feel the same force no matter where it is. So that's another reason why we would say that this is a uniform field. Now we're going to have a look at how you can actually calculate the force on an object, or the force of attraction between two particular objects from a gravitational point of view. Newton first came up with this, which is why it's called Newton's law of gravitation. And if you want a definition in words, it's given by this thing here. So the force of attraction between two objects, because gravity is only ever an attractive force, it never repels, so it only ever attracts. So the force between these two objects is proportional to the mass of both of the objects. So the more mass there is, the bigger the force, and it's inversely proportional to the distance between them. And it's actually inversely proportional to the distance squared between them, like that. So basically, if we increase the distance, then the force will go down. So in terms of an equation, then it's given by this, where F is our gravitational force. And as you know from GCSE and from Unit 2, force is measured in newtons. M1 and M2 are the masses of our two objects. So that's the mass of object number 1. This is the mass of object number 2. So mass 1, the mass of this planet, mass 2, the mass of this planet, and then r squared, well, r is the distance between these two objects, like this. And if these are kind of extended objects, so if they're like planets, then we would measure the distance from the center of this planet to the center of this planet, not from the edges. So it's from the center to the center. And so we've got r squared, so this bottom thing is the distance squared. So the whole of the bottom would be measured in meters squared. Now there's a constant of proportionality as well. There's this here. It's called Newton's gravitational constant. It has a value of 6.67 times 10 to the minus 11, so it's really small, and the units are Newton meters squared kilogram to the minus 2. So there's quite a lot on there. You can see that this number is really small, and that's basically why we only see gravity acting over really big scales. If this number was much bigger, then the force of gravity would be much stronger, and so we would see the effects more and more the bigger this number was. But because it's so small, we only see then the gravitational force is actually relatively small compared to, for example, the electrostatic or the magnetic forces that we'll have a look at later on. Now, this particular relationship, because it's inversely proportional to the distance squared, these kind of relationships are given a special name. This is an example of an inverse square law. So, inverse square law, and these pop up all the time. You'll see later on that, for example, capacitors and also to a certain extent certain things to do with nuclear physics and things like that, they all contain some sort of inverse square law, not to be confused with exponential decay, but inverse square laws have a graph that looks something like this. Basically what we're saying is as this variable increases, this one drops down. So in this case, if we had, for example, the force and we kept these two masses constant and we varied the distance, then the further away we go, then the smaller the force becomes. And in actual fact, it's very important to know that if you double this distance, then the force will go down by 4. Because you've doubled it, it's gone up by a factor of 2, but because it's squared, it's gone up by a factor of 2 squared, so the whole force goes down by 4. If you triple this distance, then the whole force will go by 9, down by 9, because it's 9 squared. If you quadruple the distance, so if this went up by a factor of 4, then the whole force would go down by a factor of 16. And it works with fractional things as well. So for example, if we started off at this particular distance and the distance increased by a factor of say 1.5, then the force would go down by a factor of 1.5 squared. So you can use that to do some kind of quick rough and ready calculations, but it kind of helps to see that if you the one I always remember, if you double the distance, then the force goes down by 4 simply because of this squared bit. So let's do a little example calculation. So let's imagine we've got two planets. The first planet's got a mass of this, the second planet's got a mass of this, and we know that, and we're told that they're 85.5 million kilometers apart. We want to know the force between these two planets. So we'll simply use this equation here and we'll put our numbers in. So we want to know the force, so we should know everything else. Well, G, as we saw before, was 6.67 times 10 to the minus 11. Multiply it by the mass of the first planet. Well, we'll take this as the mass of the first planet. So 8.55 times 10 to the 24. Multiplied by the mass of the second planet, which is this here. So 6.11 times 10 to the 24. And then we divide it by the distance squared. Well, if we take this, let's just do it over here. We've got 85 million kilometers. So we'd need to multiply by million, so 10 to the 6, and we've also got kilometers, so we'd have to multiply by 10 to the 3, would give us in meters, and if we write that in standard form, it gives us 8.55 times 10 to the 10 meters. So that's that's the distance between the center of this planet and the center of this planet. So if we pop that into our equation like this, and then one of the most common errors that people make when they're actually doing this calculation is to forget the squared bit, so we have to make sure we put the squared bit on, and then it's just a matter of working it out on our calculator. And so if we multiply those numbers together, divide by this squared, we end up with to two significant figures, 4.8 times 10 to the 17 newtons. So that's the force that each of these planets feels because of the other one. So that's the force of attraction between these two planets. So this one will feel a force pulling it in this direction of this, and this one will feel a force in this direction because of this planet here. So that's really the basics of gravitational fields. We had a quick look at the difference between a radial and a uniform field. We introduced Newton's law of gravitation and had a very quick look at why it's called an inverse square law, and then we've just done an example to have a look at how you actually use Newton's law in order to calculate the gravitational attraction between two masses. So that's it from me, and I hope to see you again soon.